The name of this video is Charged Loop. This is the first example we are going to encounter on continuous charge distributions. This is a very simple one, yet a very useful one. The problem is very similar conceptually to that of the hexagon. In that case, though, we had a discrete charge distribution with 6 point-like charges, which were contained within a circle. In this case, we are going to consider that circle and assume that there is a uniform charge distribution with a continuous distribution on that circle. So again, the scenario is we have a circle of charge, like this one here. I will sketch it now. We are in 3D, so this is the circle, and we are attempting to find the electrostatic field on the central axis, the axis that is normal to the plane of this circle, that contains this circle, into the center of the circle. Okay, so how do we proceed? First of all, we want to make a nice sketch. So I'm trying to render this in 3 dimensions, and so the circle, I'm going to represent it as an ellipse, as I've done for the hexagon of charges. So I want enough space down here, so let's attempt to do our circle here. This ellipse is in 3D, looking at it with an angle. The circle of charge I want to consider. The center of the circle is right there. The radius of the circle is capital R. This circle is characterized by a linear charge distribution. This linear charge distribution is uniform, which means, since it's uniform, we have a constant charge density, so uniform distribution with a constant charge density lambda. Okay. So we want to find, as in the problem of the hexagon, the electrostatic field on the central axis, so somewhere here, in a point capital P, on the central axis of this object, okay, of this circle. So note that if lambda is uniform, we can rewrite it, in this case, very simply as the overall charge Q contained in this circle, suppose it is Q, divided by 2 pi capital R, which is the length of the circle, because it's a uniform distribution. So it's very simple. We just divide the total charge by the length of the circle, which is 2 pi R, 2 pi capital R. Okay, so that's what we have for lambda. And so we want to find the electrostatic field at this point here in space, okay? So I will rewrite this question in a minute after the rest of the sketch is done. So we want to find the electrostatic field at point capital P. How do we proceed? As always, we need to follow the 4 steps which I already outlined in a previous video. So the very first step is to identify, to choose a proper coordinate system for this problem. In this case, the coordinate system is, again, like for the hexagon of charges, a cylindrical coordinate system. So we're going to have this as our z-axis. The r-axis, for example, will be this. This is the origin of this coordinate system. And the 0 for the angle var phi, we choose it at this location here. So here var phi is equal to 0, and var phi from 0 is counted in this fashion, counterclockwise around the z-axis. Okay, so now we want to project, so let me rewrite all the steps so we don't forget. Step 1 is the coordinate system. In this case, we have chosen an origin R, var phi, z, a cylindrical coordinate system. Let's project it downward here so we can look at this problem from the side. So again, the way this works is that we have a circle. we want to find the electrostatic field normal to this circle. And now I want to look at this problem from the side. So this is the projection I'm doing here. So in order to do that, do this. Okay, this is the axis where we want to find the electrostatic field. So down here, we're going to have the side view of this loop of charge, where again this distance here is r. This is the origin, the center of this object. And so let's sketch our OR bar phi z coordinate system again from the side view. This will be our r, and this will be our z axis. This is the origin down here of this coordinate system. And I'm not showing bar phi, which goes in this direction counterclockwise, again around the z-axis. So now that we have a proper coordinate system, the next thing we want to do is to identify all the forces or the electric fields, the electrostatic fields for this problem. So we want to find the electric field at point capital P and sketch it. So this is our question mark. Okay, so in order to do that, let's do this in red as always. So let's pick our point capital P, let's say somewhere here. This is our point capital P. Now we know from Coulomb's law that, okay, now we have a continuous charge distribution. So how do we proceed? In the case of a discrete charge set of charges, it was kind of simple. So we consider one charge and we try to see from Coulomb's law what is the effect of that charge, of that point-like charge somewhere in space. We need to do the same thing in this case where we have a continuous charge distribution. So for example, we can consider the infinitesimal neighborhood of length dl around this point here. So this dl will be characterized by a certain charge dq. This charge dq is given by lambda times dl, the density times the length. But this actually can be further written as lambda, what is an infinitesimal element on a circle in a cylindrical coordinate system. Well, it is the radius capital R times d bar phi. So lambda times capital R times d bar phi is the infinitesimal charge of this little infinitesimal element in the neighborhood of this point. Similarly, if we choose another neighborhood exactly opposite of this here, we will have a dq also associated with this little piece of length dl. Each of these two pieces of length dl behaves effectively as a point-like charge in space. So we can use for each of them Coulomb's law to find the electrostatic field dE, which is infinitesimal dE, associated with one of them. So if we consider the first element here, for example, from Coulomb's law, we know that the electrostatic field has to be directed on the line, on the straight line, along the straight line which connects these 2 points. So this will be, for example, the electrostatic field dE at point capital P due to this charge, and let's call, for simplicity, this charge here, we call it dq left, whereas the charge here we call it dq right. And so this one is dq left here, and so this one we'll call it dE left. Okay. Similarly, if we consider here dq right, if we consider dq right from Coulomb's law, we know that the force, the electric field, the electrostatic field, has to be directed along this line, which connects the observation point, the test charge, from the source charge. And so we obtain this vector here. So this will be the electrostatic field D, E, at point capital P due to the right element, to the element on the right. All right. So now that we know all that, in this specific case, in the case of the hexagon of charges, we had 3 pairs of such point-like charges. In this case, we're going to have an infinite set of such pairs of point-like charges. With charge dq, left, comma, right. So we have an infinite set, dq left, dq right. Okay, so an infinite set of charges. Okay, what is the third step that we need to do to solve this problem? The third step is to attempt to find the degrees of freedom. Obviously, this is very similar to the problem of the hexagon. Since we have instead of 3 pairs of opposite charges, instead of 3 pairs in the hexagon, we had 3, right? So 1, 1, 2, 2, 3, 3. Now we have an infinite set of such pairs, but the concept is the same. So for the same argument we had in the hexagon, we made for the hexagon, the z component of the fields for each pair sum up, whereas the r components cancel. Therefore, we expect the degree of freedom, which is the axis along which the particle at point capital P can accelerate, is again z. So the particle cannot accelerate when placed along the vertical axis of this circle, cannot accelerate along this axis, nothing else. Okay. And again, this is due to the symmetry of the problem. We will come back to symmetries again in a few videos from now. The last step is to actually solve the problem by means of Coulomb's law and the superposition principle for continuous charge distribution, which means in this case, so PR stands for principle, which in this case means to integrate. Okay, so how do we proceed in this case? Well, first of all, we want to find the electrostatic field due to one infinitesimal charge, point-like charge dq. So this field will be dE at point capital P, which is given by 1 over 4 pi. Let's do it completely general, 4 pi epsilon naught. Then we are going to have the charge dq, which is lambda times r times d bar phi. So lambda times dl, which is r d bar phi, capital R d bar phi is our charge dq. This has to be divided by the distance square between the source charge and the observation point. Let's call this the Greek letter z. And so it has to be divided by z quantity square. And then we need to decompose. Suppose that this angle here is called theta, which is the same as this angle here. Similarly on the other side, these are all theta angles. If all these angles are theta, we will have 2 components. One is cosine theta. The cosine theta component is actually the one which goes along the z-axis, so uz. Plus, in general, there is a sine theta component times ur. And now we want to show that this one cancels out. We already know from this argument of the degrees of freedom that we should not have this one. So we expect this quantity to go to 0, this component. Now, when we integrate, we can formally show that. In fact, if we look at this problem here, we need to integrate. What is the variable of integration? Only var phi. So it's pretty simple. Okay, it's only var phi. So var phi can go from 0 to pi, and then from pi to 2 pi. Of course, in general, it eventually has to go from 0 to 2 pi. Okay. So if we consider only the region going from 0 to pi, this part here, okay, in this case, we are considering elements, infinitesimal elements on this part of the circle. And so we are in this region, and somehow when we look at the dr components, they point opposite with respect to the direction of r. So r points in this direction, right? Because we are moving r like this. But the field generated goes in the opposite direction, so it's minus dr from 0. So from 0 to pi, we have a minus for this contribution. So now we already know that this sine of theta component will go to 0 from the argument about the degrees of freedom. However, we can more formally show that. So let's integrate using the superposition principle to obtain the electrostatic field E at point capital P. We obtain 1 over 4 pi epsilon naught, as always. Lambda, capital R over d squared are constant, so we can keep them outside the sign of integral. We then have, let's open a bracket, the cosine of theta term. So this will be the integral from 0 to 2 pi in d phi, in d bar phi. So we are going from 0 to 2 pi. Cosine of theta, we have seen this already for the problem of the hexagon. It's nothing but regular z divided by Greek z. Times uz. Now, in order to write down the sine of theta UR component, we can either integrate from 0 to 2 pi or integrate from 0 to pi 2 times. So the first time we just consider this r here. So this r, we say that it goes from 0 to pi. Okay. So here is the negative side of r. So this is the origin. Here we are positive, here we are negative. So if something points in this direction is positive from 0 to pi, and in this direction is negative. So all these charge elements from 0 to pi here, they will generate a field which is obviously pointing in the opposite direction with respect to r from 0 to pi. So this will be negative. So we're going to have a minus integral from 0 to pi, okay, in d bar phi of the sine of theta, which is capital R divided by z times ur. Interestingly, the elements on the opposite side here, the infinitesimal elements on the opposite side, from 0 to pi, generate an electrostatic field dE, which is in the same direction as r. So this is plus the integral, still from 0 to pi, d bar phi, capital R divided by Greek z ur. Okay, note again that we have chosen to go from 0 to pi. Since effectively we need to go from 0 to 2 pi, we need to calculate these 2 times so that we account for both elements on both sides with this minus sign. And so obviously, since the integrands are the same, these 2 quantities go to 0, which confirm the degree of freedom has to be only z. All right. So now we can finally obtain the total electrostatic field at point P, where we use again Coulomb's law, the superposition principle. Z over z, the normal z over the Greek z, we can take it outside. So we know that Greek z from the Pythagorean theorem is nothing but capital R squared plus normal z squared under square root. Okay, so we obtain the usual structure similar to that obtained already for the hexagon of charges, 1 over 4 pi epsilon naught. Then we have lambda times capital R times z, the integrand, we can take it outside. The only variable of integration is d bar phi, divided by Greek z to the power of 3, okay, square plus 1 is 3, z we have it, and finally we have the integral between 0 and 2 pi of d bar phi, in d bar phi, okay, and the whole structure here, the whole field goes in the uz direction. And so to conclude, this gives me 2 pi, and so I obtain the overall charge. 2 pi lambda capital R is nothing but the total charge Q, and so we can write this quantity as 1 over 4 pi epsilon naught times, you can express it either as a function of the lambda, so let's do that. So we have lambda capital R z times 2 pi divided by z, Greek z to the power of 3. It's actually capital R squared plus z squared to the power of 3/2, the usual 3/2, along uz. And if you want, we can rewrite this as 1 over 4 pi epsilon naught. This is the total charge Q from this definition here. So we end up having Q times Z divided by R squared plus Z squared power 3/2 along the UZ direction. For example, in this case, at Z equals 0 in the center, we obtain a zero field. I leave a couple of questions that I want you to discuss in Piazza. The first question is, what happens? So the first question is, what happens when again we go in the case that small z is much larger than capital R? So what happens to the E field at point capital P in this case? And the other question is, what happens when z is smaller than 0 to the field E at point capital P? So let's discuss this in Piazza as always. I want you to discuss about this in Piazza. Okay? All right, so this was our first problem on a continuous charge distribution. It was a charged loop. So it's a loop of charge, okay, here, where we want to find the electrostatic field on the vertical axis, at the point capital P on the vertical axis. Our source charges are on the loop, and at point capital P, we have the test charge, okay? So as always, we identify the coordinate system, cylindrical coordinate system. We sketched, looking at the symmetry of the problem, for an opposite pair of point-like charge particles of infinitesimal charge dq, the components of the infinitesimal electrostatic field dE. We then, from that, attempted to find the degrees of freedom, which we verified at the end by means of this calculation. And finally, by means of Coulomb's law, for one infinitesimal dq point-like charge particle here, we found this law. This is Coulomb's law for an infinitesimal charge. And eventually we integrated it, which means we applied the superposition principle to obtain the final result, okay, where we verified that there is only, in fact, a UZ component to this electrostatic field. And so I will see you in the next video, which is a little bit more complicated problem about continuous charge distribution instead of the infinite straight line, a very important problem. Thank you.